Welcome listeners again to the series of lectures on the fundamentals of geology, and we'll be discussing on the concept of crystallography, which is also a very important concept in the subject of geology. And I am Dr. Shandeep Banerjee, a faculty member of Department of Geology in Banaras Hindu University, Varanasi, and I have been discussing with you about the origin of the universe, origin of the solar system, followed by the geological time scales, and also the concept of continental drift, plate tectonics, formation of oceans, and other things till now. So here we will now plunge into the subject specific concept of crystallography, followed by mineralogy, and then further about 5 or 6 lectures from now we will be also talking about different rocks that are occurring on the surface of the earth. So starting with the first part of these 3 lectures related to crystallography mainly. So as the name suggests, crystallography, it is kind of rhyming with another subject name that we all know and we have read in our school life as well, that is geography, which means the mapping of the earth. So likewise, crystallography means mapping of crystals. But before going into the details of how we map crystals and how we look at crystals of different minerals, first we need to know that why we need to study crystallography. Though specifically we will be dealing on the geological perspective of crystallography, but crystallography is a fundamental concept that is also very much essential to understand various concepts in solid state chemistry as well as in different aspect of your material sciences. So now to look for the answer that why we need to study crystallography, crystals may occur at varying scales, like we can see in this first simple figure, that there are large scale crystals that are present, and you can also compare the scale of this human being who is standing here, and you can simply compare you can say these crystals are huge in comparison to this man standing here. So you can say these crystals are about 30, sometimes 40 feet long in this particular area. Similarly, you can also have smaller crystals of different minerals, like we can see a few crystals that are present here of a particular mineral. Also, crystals can be observed under microscope. So it is obviously a factor of scale that whether your crystal is a large one, it's a hand specimen scale a crystal, or it's a microscopic crystal of a particular mineral. Now, if I look at the various application of crystallography, we all know that like India is an agricultural independent country. Here also there is a there are huge implications of studying crystallography, because for making specific fertilizers which are essential for the growth of different agricultural plants, you need to know the structure that is present, or which make up or which are the constituent materials of your fertilizers, which are definitely or they will be used in field, and they will also control, depending on the crystal size as well as the composition of the crystal, it will also control or supplement the growth of various agricultural plants. Similarly, if I look at the second example on for example, the purpose of drinking water. So nowadays getting a clean drinking water is obviously hard. So generally we always use some kind of filter or some kind of be it an gravity settling filter or be it an electrical one. It is basically based on the concept of your osmosis or sometimes reverse osmosis, and for that you need certain films or certain you can say certain material through which the water will pass through and the impurities will be separated from the rest of the water. So, for that also you need to have an idea about the crystal structure of the material that is being used as a separation between the you can say the purest or the pure form of water that is getting separated from its impurities. Then you also have a larger implication when we talk about concretes or building materials. As we all know again that the composition of the building materials are assigned in such a way that they can withstand large strengths, as well as sometimes it is not only about the strength, it is also about the durability of the material. So, you need to have a clear understanding that under in which scale or under some boundary conditions, how your each and every crystal of a particular mineral, be it your concrete, be it your normal bricks or the artificial bricks that are being prepared, they need to have a particular crystal structure, and by varying this crystal structure you can play with the strength and the durability of the materials. Also, if I simply, as we have all now or we are now all dependent on the mobile phones, be it a normal mobile phone, be it a smartphone, obviously it contains various electronic materials, and again the structure of the electronic materials is also governed by the different concepts of crystallography. And so be it your smartphone, be it your large windmills that you can see for the purpose of generating electricity, or even your aeroplanes, all these materials that are used to develop or to you can say create this be it a mobile phone, be it a windmill, be it an aeroplane, are all actually controlled or governed by the idea that how you can play or how good you know your crystal structure of a particular material that you are using to create some material for that will be used for our daily livelihood. So, you can say that crystallography is essential in our daily lives. But here I would like to now go, because being a geologist, we need to see the geological purpose or the geological perspective of different materials, and specifically when we are talking about geological materials, we are actually talking about minerals and rocks that make up the earth. So, here you will be having three parts of this lecture with three lecture goals. The first one, obviously, in this lecture we will be discussing about the crystal properties. Then in the second part of this same lecture we will discuss about the symmetry in crystal, and in the third part of this lecture we will be discussing about crystal system. So, starting again with the idea that the crystallography means, it means obviously, like I was saying, it means the mapping of crystals. So, here also you can see a crystal of a diamond, a crystal of this is a particular mineral named as pyrite, and here also you can see a crystal of quartz, that is you can see say the most abundant mineral that you can find. Then there are several flavors of crystallography. The first one is obviously X-ray crystallography, followed by optical crystallography, and the third one is geometrical crystallography. So, in case of X-ray crystallography, what we do, we generally take the powdered form of certain material and we try to interpret the composition of that material by the concept or applying the concept of X-ray diffraction based on the formula that you might have read in your school life, n lambda is equal to 2d sin theta. So, from the diffraction angle you can assign the composition or you can even decipher the individual constituent of a mineral or any material under study, and this concept was pioneered from the you can say the rule of X-ray or the law of X-ray diffraction put forward by Lawrence Bragg and his father, and for this concept of X-ray diffraction in 1915 Lawrence Bragg also got the Nobel Prize. So based on the established X-ray diffraction, or based on this 2 theta angle, every mineral has been determined over the time. And now if I say, for example, I am looking at an unknown mineral or an unknown rock, then I can again make a powdered form of that mineral or that rock, and then I can also find out the 2 theta angle with the idea of the X-ray diffraction using an XRD instrument. And from that you can compare the established 2 theta angle of all the minerals and that could be present on the earth surface, and then you can simply compare the 2 theta angle and you can comment that whether that material is quartz or albite or diopside. These are different minerals you can that we will be also discussing when we will start our discussion on minerals. Then the second flavor, that is optical crystallography. It is solely based on your observation, and that can be carried out with the help of an optical microscope. And there we generally use thin sections that are prepared by slicing some mineral or some rocks, and they are, you can say, grounded to such a level that light can pass through that thin film of that mineral or that rock, and generally it is around 0.3 mm thickness. So that is your utility of optical crystallography, and from those thin section you can also assign or try to at least have an idea about the crystal structure of a particular mineral. And the third flavor, that is your geometrical crystallography. This is solely based on the idea of symmetry theory. So we will be discussing symmetry theory in detail in the second part of this lecture, and it is generally done on the basis of the geometrical features that you can observe specifically in a mineral or in a crystal, to be specific. Obviously a crystal will belong to some mineral. So you can have an idea of the geometrical parameters or properties of a particular crystal. Now for crystal properties, that is the focus of this first part of this lecture, we need to define what a crystal is. Again, to start with, that crystals, if I would like to define it, then crystals can be defined as a homogeneous solid bounded by naturally formed plane surfaces. Like this, you can see a revolving crystal here, where you have these planes which are planar or plane surfaces that are bounding some space within it. So these plane surfaces are termed as faces, which can be related to a regular arrangement of the atoms. So here also you can see that these atoms, or sometimes the molecules, they are placed in a very regular fashion. So this is nothing but crystals are a reflection of its, the geometry of a crystal is nothing but a reflection of its internal arrangement it is already possessing. So again, to define, crystals can be defined as a homogeneous solid bounded by natural formed plane surfaces termed faces, which can be related to a regular arrangement of atoms. Then and there is another terminology which is referred to as crystal form. Crystal form is nothing but it is the assemblage of crystal faces related to each other by the symmetry that the crystal possess. So obviously we will be talking about your symmetry, different types of symmetry in the second part of this lecture, but just to think about that crystal form, whenever we are looking at the crystal form of a crystal, it is no longer it is a single face that we are concerned about. We have to take into consideration all the faces, or a set of faces at least, which are bounding that crystal. Then there is another terminology, that is crystal habit, and that can be defined as the general aspect or shape that a crystal possesses, which is produced by relative development of different forms. So now if I just take an example of a crystal model like this, then you can say that if I am looking at a crystal like this, then these are the faces that are bounding the crystal itself. So definitely it's an wooden model, it is not a real crystal, but just to mimicking the real condition, you can simply think of that these are your planes, which are obviously flat surfaces or planar surfaces which are bounding. There are also planar surfaces on the top, again there are planar surfaces in the bottom. So obviously it's a crystal that is being bound by a set of 12 faces, 4 at the middle, 4 at the top, 4 at the bottom. So this is a crystal, and there are other geometrical parameters. We'll talk about that in a bit. So, and now if I say that these 4 faces are making up means assemblage of faces, then this will be considered under crystal form. So we'll also talk about crystal form in the third part of this lecture. So now if I look at the different morphological parameters of a crystal, then the first one that we have just seen, that your flat surfaces that which are defining or bounding the crystal are your faces, like this you can also see in this diagram. Then you also have edges, which are nothing but the intersection of 2 adjacent faces, like we can see this one is adjacent to this face is adjacent to this one, this face is adjacent to this one. So these are your edges that are being formed due to the intersection of the faces. Then you also have a different parameter that are referred to as solid angles. So solid angles are not normal angles. Obviously, to form a solid angle, which are also sometimes referred to as vertex, you need at least 3 or more plane than that. So if I say that I am looking at a vertex like this through which I am holding this crystal, you can say that these 4 faces are making a solid angle, which is the vertex of this crystal, or which you can also say the apex of this crystal. So these 4 faces are subtending an angle or in between in the crystal, which is defined by the presence of the apex, and you can say that this is a solid angle. So based on these 3 morphological features, again Euler proposed a formula that whenever we are looking at a crystal of any mineral, doesn't matter what the mineral is, this particular equation should hold, that the number of faces, if I am looking at the number of faces, for example, you can think of a cube where you have 6 faces to define a cube. Then you have the presence of solid angles that are represented as the corners of the cube. So obviously there are always 3 faces that are intersecting at the corner of the cube, and you can say there are 8 solid angles in it. So the number of face is 6 and your number of solid angle is 8. So in total you have 14 on the left hand side of this equation. And if I again think about the edges of a cube, then you can see that there are 12 edges in a cube, plus always a constant of t. So again on the right side you can say there is again the value is coming as 14. So the number of faces plus the solid angle should be always equal to the number of edges plus a constant of 2 for your naturally developing crystals. So this equation you can apply from time to time for both theory and practical purposes, and you can say that whether means your assessment of the number of faces, or the assessment of number of solid angles, or the assessment of number of edges is correct or not, because always crystals are not as simple as that of a cube. There could be multiple faces, there could be 36 faces, there could be 96 edges. So there are different examples of complex faces, complex crystals as well. But always you can simply apply this formula and check whether your assessment about the face, solid angle and your edges is correct or not. Then there is another morphological feature which is again extremely important, that is your interfacial angle. And the interfacial angle may be defined as the angle between any 2 adjacent face of a crystal, like this, like I was referring to this crystal earlier. Then these 2 are your adjacent faces, you can see this one and this one, these 2 are your adjacent faces. So the angle between these faces will be your interfacial angle, not just angle between any 2 faces in the crystal. You have to always consider the angle between the adjacent faces. So that will define your interfacial angle. So in crystallography, the interfacial angle of a crystal is the angle subtended between the normal drawn on the 2 faces, and for this we generally use two kinds of instruments. For larger crystals where you can place instrument like this one, you can see there is the contact goniometer. It simply works like a protector from a geometry class in school, but it has a rotatable arm that is attached to this protector. So what we can do, we can simply, if I want to find out the angle between two adjacent faces, what I'll do, that I can keep one arm on one face and the base of the protector on the other face, and simply I can read it like we do between two lines using a simple protector. So that is the same concept can be utilized here with the help of a contact goniometer. Why contact? Because you are placing the arms of the goniometer on contact on the surface or in contact with the surface of the crystal. So likewise, we can simply use this, you can say, a modified version of your geometrical protector that we generally use in geometry, and you simply can measure the angle between two adjacent faces. The other type of goniometer is a reflecting goniometer, where your tiny crystals, if the crystal size is very small, then you really can't place the contact goniometer on the surface of the face. If your crystal is like this, then you can't really place the arms of the contact goniometer on the crystal face. For that, we use reflecting goniometer. So reflecting goniometer is a setup. It is not a complex one, obviously. So there is a small you can see a small space for keeping the tiny crystal, and there is a light source. Also there is a rotating stage at the bottom of the crystal from where you can read, and what you will be reading, you will be looking through this means ocular lens here, and if when I am rotating the crystal, what will happen, that the surface of the crystal will reflect light from it, but the edges of the crystal will not reflect any light from it. So a light source has to be there. So when you are rotating the surface of a crystal or the adjacent faces, so when the light is obviously getting reflected from this face and coming onto your eye, then you can see the face, you can take the reading from the rotating stage, which is placed just below the crystal, and as you simply turn the crystal or you go to the adjacent face of the same crystal, what is happening, when you are turning it, at the edges there will be no reflection, but again to the adjacent face there will be reflection. So again you can take the reading from this rotating stage, and then you can simply subtract this reading from the smaller one from the larger one, and you can again find out the interfacial angle. So strictly speaking, contact goniometers are used for your larger crystals. Reflecting goniometers on the other hand are used for smaller crystals. We don't have a reflecting goniometer right now to show you, otherwise I would have shown you. Then some other morphological features of a crystal, like a set of faces whose mutual intersection gives rise to parallel edges like this. So there are a set of faces you can see, and they are also giving rise to, at the intersection of the faces you are getting edges. So if there is one imaginary line that is chosen within a crystal to which the set of parallel edges of a zone are all parallel, then in the line or axis to which these edges are parallel is called a zone axis. And also in this case you can see that if I mark this axis as C axis, then this will represent or this will be your zone axis for all these three faces. Now coming into the other geometrical parameter, anything that you can quantify needs certain parameters to quantify. So in a crystal, if I am willing to quantify specific faces, and I want to see that how a face is oriented in a three-dimensional reference frame, then you need to obviously quantify faces, and this quantification is based on two parameters. The first one is Weiss parameter, the other one is the Miller indices or Miller index. So your crystal parameter is the relative distance that a face cuts on the crystallographic axis of that face. So always in crystallography, remember, we are talking about a 3-dimensional reference frame. So if one face is cutting all the 3 axes like this, then it will cut at certain unit distance of, for example, A axis, that is going in from my end to your end. Then you have this B axis which is going parallel to me, and you have this vertical C axis. So in case of hexagonal crystals, there are 3 horizontal axes, 1 vertical axis, but for the rest of the minerals you generally have 2 horizontal axes and 1 vertical. Sometimes the vertical axis or sometimes the horizontal axis are also inclined a little bit, that we will be discussing in our third part of this lecture. So in other words, crystal parameters are the ratio of the intercepts. So you can see there is a face, the solid one as well as the dotted one, and they are having different intercept along the A axis, B axis and the C axis, and the ratio of the distances on the faces from the center of the crystal. So the distance from the center along individual axis will define the unit distance. So it is not necessarily essential that always your axis, A axis, B axis and C axis will have same unit distance. The unit distance of a particular axis in a crystal might also vary. So the 2 methods, like I was mentioning, Weiss parameter and Miller index or Miller indices. So the first one, if I apply this face that is having a solid line A, B and C, this one, then this one, for example, is cutting 1 unit of A axis, 1 unit of B axis at B and 1 unit of C axis at capital C. So that is the Weiss symbol 1A, 1B and 1C. So that is the Weiss symbol or the Weiss parameter of that particular crystal face. Similarly, if I take this dotted face now, or the discontinuous line that you can see, so in this case your capital D or the face is cutting at 1 unit distance of A axis at capital A or capital D. Then this one is cutting at 2 unit distance of B axis, which is represented as capital E, and you also have the half intercept of the C axis, which is represented as F. So here you have this Weiss parameter of 1A, 2B and half C, but it is always not easy to keep the reciprocals or keep the fractions of some measurements. So what Miller did, being a civil engineer, what he did to simplify things, he simply took the reciprocals and clear out the fractions. So if I start with Weiss parameter of 1, 1, 1, then I can simply take the reciprocals 1 by 1, 1 by 1, 1 by 1, and the Miller symbol will be 1, 1, 1. But remember always that Miller indices of a face are kept in first brackets. So for DEF face, you have the reciprocals of 1A, 2B and half C as 1 by 1, 1 by 2 and 1 by half, that also means 2 by 1. So now your Miller indices for this particular face that is represented as DEF is your 214, which is again has to be kept in first bracket. And also based on the same concept, your indexing of any face can be done. So a face that is cutting only the A axis, for example, will have a Miller indices of 1, 0, 0, because 0, why? Because it is cutting the B axis at infinity, it is also cutting the C axis at infinity. So that's why the reciprocal, if I take, then it will be obviously 1 by infinity, which is also will come back to 0. So that's why the Miller indices of a face which is only cutting the A axis will be 1, 0, 0, which is only cutting the B axis will be 0, 1, 0, which is only cutting the C axis is 0, 0, 1, and if it is cutting all the 3 axes, then the simplest example is 1, 1, 1. Then also you can calculate zone symbols, but we'll be again discussing with zone symbol in the second part or in the third part of this lecture. So just to summarize the first part, we have looked into the different types of crystallographic study: crystal, its definition and idea; crystal, its form and habit; then crystal morphology, and also the crystal parameters like the Weiss parameter and the Miller indices. And just to before I conclude the first part of this lecture, I would like to give you a simple historical perspective that the molecular structure of penicillin was determined during World War II by Dorothy Hodgkin using crystallography. And due to this, you can say discovery, chemists could start the quick synthesis of this compound, thus saving millions of lives during the Second World War. So, I'll like to conclude the first part of this lecture on crystallography. Thank you. We'll continue with the second part.